So let's discuss yung aking binigay na module last week. Yung shear and deflection of beam. So we have here the shear. So as we know, we have two types of shear stress being developed sa ating beam. Meron tayo ng tinatawag na vertical shear stress or yung tinatawag nating vertical direct shear stress, and meron din tayo ng tinatawag na horizontal shear stress. Okay? So pagka vertical shear stress, yung ating VA, so this will be for the vertical. So for our vertical or direct shear stress, yung ating V over A, syempre alam nyo, stress is equal to the load over area, di ba? So yung direct shear stress natin is V over A. Wherein, ito yung magiging equation natin for vertical shear stress. So pagka wide flange yung section or I-shape yung section natin, yung area which is responsible for our, for example, we have here wide flange or I-beam. So pagka wide flange yung section or I-shape yung section, yung area na responsible for shear is actually the area of the web lang. So ito yung web natin. So yung area dito lang ang responsible for our shear stress. Okay? So ito yung ina-assume natin na nagre-resist ng shear when we have an I-shaped section. Yung portion dito, yung portion dito ng flange, pati dito sa baba, in reality, meron naman siyang resistance. Kaya lang, very minimal yung resistance niya against shear. That's why, nine-neglect natin in the analysis for shear, yung effect nitong, ito, yung wide flange, yung flange natin dito sa area na ito. Okay? So, bali nagko-concentrate na lang tayo sa area mismo, sa pinakapuno ng ating section. Ito, which is our D. So, this is our depth. Mula dito hanggang dito. And then yung thickness ng web. Kaya yung area na kino-consider natin dito is the area of the web, which is actually equal to D over TW. Okay? And yung ating pangalawa naman, yung ating pangalawang consideration sa ating shear is yung tinatawag nating horizontal shearing stress. So pag maalala nyo pa from your strength of materials, if you could still remember, yung equation natin for the horizontal shearing stress developed is equal to this value. So for this is for the horizontal. Okay? So ito yung ginagamit natin for horizontal shearing stress na equation. So ito yung direct shear stress sa web natin. Pag I-shape, Y-flange, and yung mga steel section natin. So, ang equation natin for horizontal shearing stress, yung tinatawag nating maximum shear, is equal to VQ times IXB. So, ito yung, pag maalala nyo, ito yung ginagamit ninyong equation sa strength of materials ninyo in computing for the shear stress. Okay? So, ang magiging Pag maalala nyo pa yung shear stress diagram natin, so for rectangular, di ba meron tayong shear stress diagram na ganito so in your strength of materials. So ito yung magiging VQIXB natin. Or yung ibang equation, yung ginagamit is yung 3V. 3V over 2BD pag yung depth and width yung ginagamit na value. Pwede din siya. So this is for rectangular. So pagka I-shape or wide flange, yung magiging shear stress diagram natin, dito sa part ng wide flange, maliit lang yung shear stress natin dyan, dito sa part ng wide flange. So lalaki lang yung ating shear stress on the part of the web. So ito yung magiging pinaka-stress natin sa web. So ito yung pinaka-stress natin sa flange. Maliit lang actually yung shear stress sa flange. Kaya nine-neglect na natin yung ating effect ng flange. Kaya ang kino-consider lang natin is the area of the web. Okay? So kung mapapansin ninyo, napakalaki ng difference ng shear stress sa web compared to that of the flanges. So that's why yung nag-govern na shear strength equation natin is yung sa web lang for the I shape. Okay? So ito yung magiging actual shear stress natin for direct shear and for the horizontal. Actually, ito yung gagamitin, palagi natin gagamitin sa steel. Okay? Yung V over area of the web or yung V over dTW. Since this is the area of the web. And this area of the web is one that is responsible for the shear for I section. Okay? So we also have here the general provision. This can be found on section 507 of your NSCP 2015. So general provision for shear, the design shear strength natin, and the allowable shear strength, Vn over omega ohm, shall be determined as follows. Okay? Such that yung ultimate natin, ito yung ultimate shear of the beam natin, yung Vu, should be less than our design shear strength. Ito yung design shear strength natin, ito yung ultimate shear sa beam natin. This is for the LRFD. And the same, yung actual shear strength natin, or yung actual shear force, should be less than or equal to the allowables, ito yung allowable shear strength natin. Okay? So, parehas rin lang sa flexural, sa tension, the ultimate is always less than or equal to doon sa ating design and the allowable. Either shear, moment, flexure, tension, palaging ganyan yung provision ng ating code. Okay? So, for the LRFD, ang gagamitin natin for our fee is equal to 0.9 and yung sa ating ASD is equal to 1.6. Okay? So, ang problema natin dito, yung ating VN. Nominal na naman. So, ito yung ating nominal shear strength. So parehas rin lang sa flexure, ang hinahanap din natin yung nominal moment. Kasi yan yung kailangan natin sa ating analysis and design. So dito naman sa shear strength, ang kailangan nating hanapin is the nominal shear strength, yung Vn. Okay? So the nominal shear strength Vn of unstiffened or stiffened webs according to the limit is equal to this equation. Yung Vn natin is equal to 0.6 Fy times the area of the web times yung ating CV. Okay? So, again, pag tinitingnan natin yung equation, medyo familiar na kayo sa Fy, sa AW, yung medyo bago lang dito is yung ating CV. Ito lang yung medyo bago dito sa ating equation. So, ano yung CV? Yung CV is yung ating web shear coefficient. Kasi sa web nga tayo nagkakaroon ng malaking shear stress. Or yung sometimes called yung modifier that accounts for buckling behavior of the web. Or yung tinatawag nating ratio of critical web stress to shear stress. Okay? So ito lang yung problema natin dito sa equation. So kasi yung 0.6 that is given by the code, yung Fy that is the grade, yung grade ng ating bakal, yung area of the web that is the depth times thickness of the web lang naman yan, so given yan sa properties ng steel. So ang bago lang dito is yung CV. Okay? So paano natin i-compute yung CV? Ito. Yung CV na ngayon yung problema natin. So marami tayong cases sa pag-compute ng CV. And sa pag-compute ng CV, okay, that based on the limit state yung kino-consider natin. Either yielding or yung buckling, yung instability. So for the case 1, this is for yielding, and for the case 2, this is for the instability, yung ating buckling. Okay? So we have here the equations on how to solve yung ating CV. So for the case 1, this is for the web of rolled I-shaped member. Okay? So yung case 1, webs of rolled I-shaped member. So pwedeng wide flange, I-shape, pwedeng S, pwedeng lahat ng I-shape section. Pwede dito sa case 1. So yung gagawin lang natin dito is i-check natin yung cases na to kung saan papasok yung ating beam condition. Okay? So for the case 1, i-check natin pag yung width thickness ratio natin is papasa siya sa condition na ito. Okay? So yung condition daw, dapat mas malaki itong equation kaysa doon sa ating width thickness ratio ng ating flange. So pag pumasa siya, case 1 yung gagamitin natin. Okay? So yung H natin dito for the standard, H is equal to the D minus 2K. So yung K natin, makukuha niyo dyan yun sa steel properties. For the H, pag build-up section naman, yung wala tayong K na given, this is, yung H kasi natin is yung andito, di ba? Yung distance, clear distance. Ito yung H natin. So pagka build up, yung H natin, D minus 2 thickness of the flange. So pag standard section, rolled I shape, ang gagamitin natin for H is equal to D minus 2K. So yung K nasa steel properties natin yan, yung value ng K. Okay? So pagka okay siya dito, so pagpasok siya sa case 1, ang gagamitin nating CV is equal to 1.0. So pagpasok siya sa case 1, pag pinag-compare nyo itong weight thickness ratio sa given na limit, pagpasok siya, ang CV natin is 1.0. And yung ating gagamitin for the reduction factor for RFD and AFD is equal to 1.0 and 1.5. Okay? So iba-iba din yung gagamitin natin for the reduction factor for LRFD and ASD sa case 1 at case 2. Okay? So pagka hindi pumasok yung ating condition ng beam dito sa case 1, move na kayo doon sa case 2. Pag nag-fail ito, hindi na na-satisfy itong equation, punta kayo sa case 2. Kasi sa case 2, for all other doubly symmetric, and I shape is a doubly symmetric. Okay? Sa case 2. Kaya pag hindi na-satisfy yung wide flange, lahat ng I-shape section ninyo or I-shape member ninyo sa case 1, move on na kayo dito sa case 2. So, ganun lang kasimple. So, pagka channel section naman, so, pagka channel section, alam niyo naman ang channel section is a singly symmetric beam. This is a singly symmetric beam. Channel, angle, lahat yan. So, pag ganito yung given na members niyo or section, dito na kayo sa case 2. Diretso na kayo sa case 2. Okay? So, yung mga T-shape, singly symmetric siya, singly symmetric and channels, diretso na kayo sa case 2 kahit hindi nyo na i-check sa case 1. Kasi yung case 1 is for rolled I-shape lang. So yung wide flange, yung lahat ng I-section. Okay? So pagka channel, angle, huwag nyo nang i-check sa case 1, diretso na kayo sa case 2. Okay? So this is for the case 2. So sa case 2, meron tayong sub-cases for the in determining the value of CV. So meron tayong tatlo dito. Yung una, pag ang width thickness ratio natin is less than dito sa equation, pag pumasok sa dito, ang CV natin is 1.0. Okay? So pagka hindi siya pumasok dito, i-check ninyo pag yung width thickness ratio natin is mas maliit sa 1.37 the square root of KV times E over Fy, or mas malaki siya. Okay? So pagka yung width thickness ratio ninyo is less than 1.37 the square root of KVE over Fy, tapos mas malaki siya dito sa equation na 1.1 the square root of KVE over Fy, yung CV natin is calculated with this equation. So ika-calculate ninyo yung value ng CV ninyo. Okay? Pagka ganito yung condition ninyo for the condition ng beam ninyo. Okay? So ito yung pangalawang CV sa pag-compute. So pag mas malaki naman yung inyong width thickness ratio dito sa 1.37, dito sa equation na ito, ang CV natin is computed by this equation. With this formula. Okay? So ganun lang kasimple pagkuha ng CV. So ang problema pag case 1 lang, madali lang siya, ang CV 1.0, or pag ito yung condition ninyo, CV is 1.0. Diretso ng CV 1.0. Pero paano pag ang condition naman ninyo, ito, dalawa yan, may equation na naman tayo, may new equation na naman tayo, which is may bago na naman tayong constant, a variable, which is yung ating KV. Okay? So alam natin yung HT over TW, yan yung width thickness ratio natin, yung Fy, yung grade ng beam, yung E, yung ating modulus of elasticity. Ito naman yung bago, yung KV. Okay? So, paano naman mag-compute ng KV? Okay, so we have here the value of KV. So, meron tayong dalawa dito for the value of KV. So for unstiffened web, so pag maalala nyo pa, yung stiffen and unstiffened web. So for unstiffened web, pag ang width thickness ratio daw natin, yung H over TW is less than 250, ang KV natin is 5. Except, so meron tayong condition dito, except for the stem of T-shapes where KV is equal to 1.0. Okay? So pag maalala nyo, yung mga unstiffened web. So ito, unstiffened yung web natin. Diba? Ito yung ating T-shape. So lahat na ng unstiffened web, pag mas maliit siya sa 260, ang KV natin is 5. Okay? Pero ang KV natin for the T-shape like this is equal to 1.0. Okay? And then for letter B, for Stephen webs naman, yung for dito, yung I natin, kasi ito, yung web natin dito is protected dito sa ating dalawa. Meron siyang dalawang support sa up and down. Kaya Stephen web tayo dito. Okay? So for the Stephen webs, ang KV natin is computed by this equation. 5 plus 5 over A over H squared. Okay? Ito yung KV natin. Pero pagka ang AH natin is greater than 3.0 or yung AH natin is greater by this equation, ang gagamitin natin KV is 5 pa din. Okay? So i-compute nyo muna ito pag ang AH natin is greater than 3 or AH is greater than this equation bago kayo pumunta dito. Okay? So pagpasok siya dito sa condition, ang KV natin is 5. This is the same here. Pero pag hindi siya pasok dito, punta na kayo dito, ang value ng KV natin is equal to this equation. Unahin nyo munang i-compute dito. So pag hindi siya pasok dito, punta kayo dito sa equation ng KV dito sa taas, which is 5 plus 5 over 8H squared. Okay? So AW, yan yung ating area ng web. Yung A, this is the clear distance between transverse stiffeners. Tapos yung A, ito yung for rolled shape, ito yung clear distance between flanges. So for build up, the clear distance between flanges. Okay? So for A, yung ating clear distance between transverse stiffener. For example, we have for example, meron tayong I shape. Yan. So pagka mahina yung ating beam against shear, yung web natin, ang ginagawa natin dyan is nire-reinforce natin siya. Nire-reinforce natin yung web. This is by providing plates na naka-reinforce dito sa ating web para dagdag support dito sa ating web na nagkikerry nung ating shear stress. Okay? So pagka ito, for example, ito yung ating I-shape. So paano natin i-reinforce yung web natin dito? By providing plate or yung tinatawag nating stiffeners or yung web stiffeners. So dito, pwede tayong maglagay dito. So pagka medyo mahina yung ating web na nagkikerry ng ating shear, gusto natin mas malakas, pwede tayong maglagay ng stiffeners or yung web stiffeners dito. So pwede tayong maglagay ng web dyan for reinforcing. Tapos meron din dito sa kabila for reinforcing. So pwede yan. So para mas mataas yung ating web. So for dito sa outer ito. So halimbawa maglalagay ka ulit dito sa middle, sa midspan ng another stiffener. Pwede din yan. Tapos meron din sa kabila. Okay? So maglalagay ka rin ng another stiffener. Ito na yung magiging clear distance between transverse stiffener. Ito na yung magiging value mo inyong A. Okay? So yung A natin, ito yung distance nung dalawang transverse stiffeners. Okay? So yung A makukuha natin dito, yung spacing ng dalawa. So yan yung ating A. So this is actually given sa problem for the analysis. So yan yung magiging A ninyo, yung distance between the transverse stiffener. Yung nilalagay natin for the reinforcement doon sa ating web. Okay? That is for the value of K. So pag meron na kayo lahat nito, H over PW, yung A over H, pwede nyo nang isolve yung K. So pagka na-solve nyo yung KV, pwede nyo nang ma-solve yung inyong CV. At pag na-solve nyo na yung CV, masosolve nyo na yung nominal shear strength, which is actually yung hinahanap natin. Okay? So far, may question ba? For the shear equation. Wala. Okay, so let's move on sa ating sample problems. So, kasali din ito sa module ninyo na binigay ko last meeting. So I hope na ni-review ninyo on how to solve for the shear. So for problem 1, we have here a simply supported beam which is subjected to a uniform service live load and service dead load, and a concentrated dead load as shown in the figure. So meron tayong concentrated dito at meron din tayong uniform load. The beam has a continuous lateral support and a 50 steel was used. So we have to check if yung given, ito yung given, yung W27 by 102 is adequate for shear. And we have to use LRFT. So given properties of W27 by 102, so nakuha ko ito sa steel manual ninyo, yung steel properties manual. So ito yung magiging beam natin. Ito yung magiging load natin. We have dead load concentrated and we have a dead load and live load uniform. So meron tayong length of full span 10 meter. Okay? So to check for the W27 by 102, if it is adequate for shear, ang kailangan natin dyan, yung design shear strength natin is greater than our ultimate shear. Okay? So pagka ganito yung condition, ito yung condition sa general provision natin, okay yung ating beam sa shear. Pero pagka mas mataas yung ating ultimate shear kaysa doon sa ating shear strength, yung beam natin is mag-fail. Hindi siya okay sa ating shear. Okay? So, ito yung magiging condition natin para ma-check natin pag adequate yung shear or hindi. Okay? So, yung ultimate shear natin, masasolve natin yan. Okay? So, ito yung pagkuha ko ng view. So, alam nyo naman yung pagkuha ng shear strength, di ba? I hope you still remember how to solve for the shear. So, yung shear diagram ko, ang highest shear ko is 477.6. So, ito yung maximum ko, ito yung ultimate shear ko. So, ito yung actual ultimate shear, which is 477.6 kilonewton. So, dapat daw itong VU natin mas maliit sa ating design shear strength, which is P times PN. Okay? So, yung P natin is hindi natin alam yung fee natin kasi meron tayong cases for dalawang cases. And for VN, this is for the nominal shear strength. So to solve for the nominal shear strength, gagamitin natin itong equation which is 0.6 FYAW times CV. Okay? 0.6 FY given area of the web, that is D. Ito yung D natin times CW. Ang problema natin is yung CV. So how to solve for the CV? So we have to determine yung value ng CV. So unahin natin case 1, that is for the standard section, W is an I shape. So unahin natin sa case 1. So sa case 1, we have to check if our width thickness ratio, H over TW, is less than 2.24 the square root of EFY. Okay? So substituting this value, since lahat naman yan given sa ating problem, lahat yan given, substitute lang natin siya. So pagka na dito, pagka na-satisfy natin yung condition sa case 1, okay, ang CV natin is 1.0. So in this case, na-satisfy natin yung case 1, which is yung ating width thickness ratio is less than 53.93. Diba? So na-satisfy natin yung case 1. So for case 1, ang gagamitin natin, P is equal to 1.0. Ang gagamitin natin CV is equal to 1.0. Okay? So meron na tayong P, meron na tayong CV, meron na tayong lahat na meron, substitute na yung values dito sa ating equation, masosolve na natin yung value of Bn. Okay? So dito, ang nominal shear strength natin, the substitute the values is equal to this value, 1865.65 kilo. So this will be our nominal shear strength. So i-compare natin yung design shear strength natin sa VU, and design shear strength is equal to the reduction factor times the nominal shear strength. Kaya pag kinompare natin yan, ito yung design natin is equal to 1865.65. Kasi nga, ang gagamitin natin P is 1.0 kasi pasok siya sa case 1 kay 1.0 ito. Okay? Pag kinompare natin yan sa VU natin, mas malaki yung ating design shear strength kaysa doon sa ating ultimate shear. Kaya yung beam natin is adequate sa shear. So, ganyan yung problem 1. So, we just have to check if W27 by 102 is adequate to shear. So, for this problem, since yung design shear strength natin is mas malaki dito sa ultimate, yung beam natin is adequate or safe sa shear. Okay? So, usually sa regular beam, standard beams natin, pag ang beam natin is pumasa siya sa flexure, kasi shear and deflection is actually continuation ng flexure natin, yung topic natin last time. So pagka pumasa siya sa flexure, kadalasan, mostly, pumapasa din siya sa shear. Okay? Now the question is, kailan nangyayari, anong klaseng beam ang meron tayo na posibleng pasado siya sa flexure tapos bagsak sa shear. So that will be possible pag ang beam natin is corbel beam, yung tinatawag nating corbel. Pag sinabi nating corbel, yung short beam lang. So this is actually short beam that is fixed at a wall or nakafix siya sa shear wall. Maikli lang yung length niya. Ito, posibleng bagsak siya sa flexure, pasado siya sa shear. Pero mostly, pag pumasa siya sa flexure, kadalasan papasa din siya sa shear. Possible lang din ito. Pwede ding pasado siya sa flexure, pasado siya sa shear. Pero possible na yung flexure niya is bagsak tapos pumasa siya sa shear. So yung purpose ng corbel, yung maikli lang yung ating length, yung purpose nito is actually patungan lang siya ng another beam. So ginagamit lang for pag meron kayong corbel din, naglalagay din lang sila ng isang beam sa taas. So yung kaya medyo maliit or short lang yung length niya. Ginagawa lang siyang patungan for another beam. Okay? So pagka-corbel kasi, pagka-drawing nyo yan, di ba, ganyan yan. And this is a very short distance. Ito yung length niya. Tapos, yung load dito, ito yung load, yung another beam. Di ba? So, pagka kumuha kayo ng moment dito, tapos meron kayong shear. Di ba? Ito yung shear niyo, ito yung moment niyo. MU and VU. So, dito kasi sa corbel, MU is not that critical. Kasi nga yung ating, syempre yung pagkuha ng MU is P times L, di ba? P times L, kukuha ninyo yung MU. So hindi siya masyadong critical kasi yung distance, yung L natin is very short. Maliit lang siya, hindi siya masyadong critical sa moment. Kaya yung corbel, pwede siyang bumagsak. Pasado sa shear, pwede siyang bagsak sa pasado sa flexure, pero bagsak sa shear. Okay? So, hindi kasi masyadong critical yung ating MU. So, that's for problem 1. Let's move on sa ating problem 2. So, for problem 2, we have here the loads given. So, a floor that carries a ceiling whose weight is 1 to 50 PA and a live load of 2.8 is made up of 120 mm thick concrete slab and 75 mm thick floor finish bolt, at which unit weight is equal to 23.6 kilonewton per meter cube, which compression flange rigidly attached to the concrete floor. We have to check if W21 by 248 and 836 steel is adequate to carry the given load considering shear. So we just have to consider shear here. So we have to assume the beam weight is negligible and the floor is simply supported by steel beam with a span of 12 meter at 3.6 meter on center. Okay. So ang given natin dito is hindi directly na load. Weight with the spacing. So kailangan nating i-compute yung total load natin in kilonewton per meter. So meron tayo yung ceiling, meron tayong slab, and meron tayong live load. So ito yung tatlong load na binanggit dito sa ating problem. Okay? So for this slab, yung slab, ang binanggit kasi dito sa slab is the thickness, the unit weight of the concrete, okay, and then the spacing. Okay. So yung spacing natin is 3.6. So para makuha natin yung weight natin, yung total weight natin, kilonewton per meter, this is equal to the thickness times unit weight of the concrete mismo times the spacing. Ito. For the slab. So yung thickness natin, mm yung given, this is in meter. Kinonvert lang siya sa meter. So, meron tayong 120 mm thickness concrete slab, tapos plus yung ating floor finish, kaya 0.195. So, 120 plus 75, 195. And so that is equal to 0.195. And for the ceiling, ang given is yung weight natin, which is 250 PA, so times the basic. Pati din sa live load, KPA din yung given times the spacing. So yung magiging total weight natin sa ating beam is equal to this value, 31.147. Okay? So for the maximum shear, pagka nakuha nyo yung total load, simple beam tayo, ganyan siya. Ito yung W natin. Ito yung total weight natin. 31.135 yung W natin. And para ma-solve natin yung ultimate load, pagka meron tayong uniform load, that is just equal to WL over 2. So yung ultimate load, ultimate shear natin is 186.88 kilo Newton. So pwede din yung i-drawing yung shear diagram. Pero pagka simply supported uniform load, this is actually yung VU natin is equal to WL over 2. Kailangan natin ito, yung ultimate shear natin, kasi i-compare natin siya sa ating design shear strength. So pagka mas maliit ito kaysa design shear strength natin, pasado yung beam natin. Pagka hindi pasado yung beam natin sa shear. Okay? So the same with the problem 1, we have to compare our design shear strength dito sa ating ultimate shear para dapat mas malaki yung shear strength natin. And to solve for the design shear strength, kailangan natin ng nominal shear strength. And nominal shear strength is equal to 0.6 FYAWCV. So wala din tayong problema sa FY area ng web, given yung properties. Problema din natin ngayon yung CV. So the same with number 1, so start with the case 1. So tignan ninyo, pag yung width thickness ratio natin is pasok sa condition ng case 1. So solving for the width thickness ratio, ano yung value natin dito? This is smaller. So I think we have, paki-solve ito. Pag totoong smaller, nagkulang ako dito. So, yung na-solve ko dito is less than yung width thickness ratio. So, kindly compute pag less than talaga ito, baka nagkamali ako dito. Wala akong na-compute na value. So, kindly solve this. 603 minus 2 times 8.5 over 27.9. Ilan ito? So, paki-solve nga ito.
15.84.
50.84. Tapos ito.
15, ma'am, 15.
63.61.
50.
63, ma'am.
Ma'am, 15.
63 points.
61.
81. Okay.
61, ma'am.
Hindi 50.84,
Ma'am,
this is
15,
63.
ma'am, dahil 15.
Yan.
15, ma'am, 15.84.
15. Tapos ito, 63.81. Okay. So, yung width thickness ratio natin mas maliit kaysa doon sa ating given equation. So, pasok siya sa condition sa case 1. So, yung gagamitin nating CV is equal to 1.0. And yung gagamitin nating reduction factor for LRFC is 1, for ASC 1.5. Okay? So, pag hindi siya pasok sa case 1, diretso na kayo sa case 2. Solve niyo sa case 2. Okay? So, given na lahat itong variables natin dito, masosolve natin yung nominal shear, which is equal to 250.37. Ito yung nominal shear natin. So, Para makuha natin yung design shear strength natin, i-multiply natin yung nominal shear doon sa ating reduction factor, which is 1.0. LRFD pa rin lahat ng ginamit ko dito. LRFD. 1.0 times the nominal shear is equal to 250.37. So, i-compare natin ito dito sa ating ultimate shear, which is 186. Mas malaki pa rin yung design natin. So, yung shear natin is, yung beam natin is adequate sa ating shear. So, for problem number 2, yung beam natin is adequate sa shear. So, pasado yung ating beam. So, that's for problem number 2. We also have here for problem number 3. So for problem number 3, we have simply supported pa rin over a length of 8 meters and it's provided with transverse stiffeners. So meron tayong transverse stiffeners space at 1,800 nm. We have to use A36, that is Fy niya is 2,400 MPa. And yung beam natin has the following properties. Ito yung properties natin sa ating beam. So D, B, F, T, F, and TW given shock. And we have to use the NSTP provision based on shear. We have to determine the value of the design shear strength. So ang hinahanap natin sa letter A is yung value ng design shear strength. So yung value ng P times yung Bn for LRFD. Ito yung hinahanap natin for letter A, yung design shear strength. So i-multiply natin yung nominal times yung ating reduction factor. And for the sa letter B naman, ang hahanapin natin is the maximum uniform distributed load that the beam can carry. So ito, yung load, yung W yung hinahanap natin. Okay? Yung W na makikerry nung beam natin. Considering yung shear, based on shear. So shear lang yung i-consider natin dito sa problem. So based on shear. Okay? So for the value of our design shear strength, i-solve natin yung Bn. Okay? Ito yung unang isa-solve natin, Bn. So, ano yung equation ng Bn? That is equal to 0.6 Fy AW P. Okay? Even yung Fy, yung AW natin, D over TW, yung CV. Kailangan natin kunin yung CV. So, we have to determine for CV. So, for the case 1, we have to check if our width thickness ratio is less than or greater than or equal to, less than or equal to 2.24 the square root of EFY. So yung width thickness ratio ko is 65.59, which is actually greater than yung equation natin, yung condition natin, yung limit natin, which is equal to 63.61. So, yung beam natin, yung condition ng beam natin sa shear, hindi siya pasok sa case 1, so i-check natin sa case 2. Okay? So, pagka na-check natin sa case 2, i-check natin sa case 2. So, H over TW is it less than or equal to 1.1 the square root of KB and of Fy? Okay? So, i-check natin yung first condition natin for the case 2. Yung width thickness ratio natin, is it less than or equal to the 1.1 the square root of Fye over Fy. So yan yung condition natin, yung unang condition natin sa case 2. Remember yung sa case 2, meron tayong tatlong condition. Yung 2.A, 2.B, and 2.C. Tatlong condition sa pagkuha ng CV. So, unahin natin yung una, yung pinakauna. So, i-check natin pag yung width thickness ratio natin is less than or equal to 1.1. Okay? The square root of KVE of Y. Wala tayong problema sa E and then FY. Ang problema natin KV. So, isosolve muna natin yung KV. And for the KV, meron din tayong dalawang condition for unstiffened web and for stiffened web. Okay? So, this is for the stiffened web tayo dito. So, given yung DBF, meron tayong TF. So, basically, ang binabanggit dito is an I shape or a wide range na I section, I shape. Kasi meron tayong D, meron tayong BF, meron tayong TF, and meron tayong TW. So, yung value ng KV natin, kukunin natin siya sa letter B. Doon sa, pag maalala nyo yung value ng KV, di ba? Dalawa yon, for unstiffened web and for stiffened web. So, sa letter A, yung unstiffened web, and letter B, yung sa stiffened web. So, yung binabanggit dito, meron tayong D, meron tayong BF, meron tayong CF, meron tayong thickness of the web. So, yung binabanggit dito is an I shape. So, pagka I shape, ang web natin is stiffened web tayo. So, punta tayo doon sa number 2. Condition for KV. Okay? So, una, i-check down natin pag ang AH natin is greater than 3.0 or yung AH natin is greater than this equation. Okay? So, nung chinek natin, ang A over H natin is 1.198 greater than 3. Chinek pa lang natin ito, hindi na siya okay. So, i-scrap natin yung KV is equal to 5. I-check natin yung equation. Yung equation wherein yung KV natin is equal to this. Yan. Okay? Kasi hindi siya pasok dito. So, pagka hindi siya pasok dito, punta tayo dito sa equation na ito. Diba? So, pag pumasok dito yung equation natin, yung condition natin, pagka mas mataas yung 3 or mas mataas ito, ang KV natin is 5. Okay? So, pagka hindi niya na-satisfy yung condition, punta tayo dito sa equation. Kindly check pala ito. 1.198 is not greater than, this is less than 3. Mas malaki yung 3 kaysa 1.98. So, paki-check din ito sa module ninyo. 1.198 is less than 3. So, hindi okay yung ating equation. So, punta tayo dito sa KV is equal to 5 plus 5 over 8H. So, pagka sinubstitute nyo lahat yan, ang KV natin, makukuha natin KV is 8.48. 8.48. So, ito yung KV natin ngayon, isa-substitute natin dito. Para malaman natin pag yung width thickness ratio natin is pasado ba siya sa equation na ito. Okay? So, pagka sinubstitute natin yung KV natin, sinolve natin, tignan nyo dito. Ito, pagka tinolve natin yan, makukuha natin, yung width thickness ratio natin is less than. Kasi 90.97 yung nakuha natin sa limit natin. Ito, 90.97. Which is actually greater than our width thickness ratio. So, kaya yung CV natin is 1. So, pagka hindi siya pasok dito, pagka for example, yung nakuha ninyo, yung H over CW, mas malaki siya kaysa ating limit na 1.1, the square root of KVE over FY. I-check ninyo yung second. Yung second natin, yung second limit natin, which is yung 1.37. Yung second limit natin. So 1.37 is square root of KB over EFY. Pagka mas malaki ito, i-check ninyo yung pangalawang condition. So since Okay naman siya sa case 2A. Case 2A, yung CV natin is 1.0. Okay? So 1.0 yung CV natin. Ang gagamitin nating reduction factor for LRFD and AFD is equal to this value. So case 2 kasi tayo. For the case 1, this is 1.0 tapos 1.5. Pagka case 2, ang reduction factor natin is 0.9 for LRFD and 1.67 for the ASD. Okay? So for the nominal shear, checking for the nominal shear, you just have to substitute Fy natin 248 area of the web, that is the D over TW, H over TWD. And this is equal to 5118.8. 5118.8. Okay? So, yung area of the web natin dito, since this is not a standard, yung H yung kinonsider natin dito. Kaya 1502. Itong AW natin. Pag mapapansin ninyo, H yung kinonsider natin dito. Okay? So, hindi standard shape yung ating section. So, meron na tayong nominal shear strength. Masosolve na natin yung design shear strength. That is the reduction factor. Ang reduction factor natin, 0.9 times the value of nominal shear. Ang makukuha nating design shear strength is equal to 4606.29. So, ito yung design shear strength natin. That is our answer for letter A. For letter B, ano yung uniform distributed load daw natin? Ano yung distributed load natin? Okay? So, ang maximum natin, VU is equal to WL over 2. Okay? Yung VU natin, this is, di ba yung VU natin is, should be less than or equal to. So yung value natin dito, pwede siyang equal sa ating design shear strength. So nakuha natin yung design shear strength natin. So ito, i-substitute natin dito sa equation. Makukuha natin yung W. Okay? Given yung left over 2. So yung magiging load natin, yung uniformly distributed load natin is equal to 1,157 kilonewtons per meter. So ito yung magiging sagot natin for letter B. For problem number 3. Okay? So that is for shear.